Yeah, I'd like to talk currently about the toolchain we are using at AVL Powertrain controls, and this is more from a supplier perspective, contrary to the OEM perspective we had in the morning. Key part from the outline of my talk, I'd like to highlight the company use case we have, and then to show you a brief overview about the tool platform we are using, and then highlight some technical challenges and also share with you some solution or best practices. Normally, I could talk hours about our tool platform, but the challenge today is to do this in 30 minutes. So please, if you have at the end of the presentation any point you want to discuss later on, feel free to contact me and we can organize offline sessions. So the business fields we are talking about is developing software for all kind of powertrain controls. And we go here from the small powertrain to the really huge part. And at the end, we have to get to provide and deliver running software. This can be only part of software components, but it can also be a full engine management system, for example. So the name of the platform we gave is AVLab. So it comes from the marriage between AVL and MATLAB. And it describes not only the tool, but also the whole platform. This is implemented in MATLAB Simulink, so it's kind of deployed in a MATLAB toolbox, but it also links a lot of tools together. The philosophy behind the toolchain we've established. So normally we don't see our key competence to make tools, to make software, but to make software at the end. And we prefer to buy a state-of-the-art tool instead of make it on your own. Unfortunately, we could not have it happen not this way, so we also made some tool for making software. But this is not our philosophy, especially to reduce the maintenance aspect. We also put great value on having an open platform. That means that we can adapt to our specific needs and be flexible. And we also want to have a platform that is, the keyword is seamless. That means without gaps between the tools, so that everything is interconnected and you don't lose the path by switching between tools. We have also a strong focus on a component-based approach, and also on the reuse aspect. So we want to be able to reuse development between different projects. And the platform should provide also a standardization and propagate the best practice within the company. So you see the triangle with the tools on the base, and then you have the methods part and the process. And the toolchain shall really support the process and the methods, and it should not be the other way around. So the use case we have regarding the toolchain from the supplier perspective, we are not so free and we have more constraints for defining the toolchain. And you see on the bubbles on the left corner, the customer is more driving the direction to the tools we have to use. And we have customers that want us to use ATAS, like a modeling tool, or we have customers that want us to use older MATLAB version. And we have customers that also want us to use D-Space Target Link as a code generator. And then other customers that want us to use a recent MATLAB version with embedded coder as code generator. So here the colors were chosen with purpose. Of course, we prefer the green scenario, where we use MathWorks products and also the most recent version. Another aspect that we have to consider when starting a project is also the delivery scenario we've defined with the customer, and also the collaboration scenario if it's requested that we can collaborate and exchange code or model together with the customer. And then I said before, we may provide only some component of the software, but we may also provide a full software system. Here a short history about the toolchain. I will not go into the details and make it really short because of the time constraint. So we started, this is important information, we started developing the platform in 2012. So at this time, there were not, for example, Simulink test for testing under Simulink. And this is the key missing feature we started implementing. And then step by step, driven by the project with the most needs and the highest priority, we added feature and feature and feature and feature, and it's becoming now pretty huge and cover a lot of the development process. And currently, we have 9 people that take care of the maintenance and the development of this platform. A strong advantage of the platform is the user base we have internally. So we have around 190 users internally, and this makes per day an average of around 30 users per day. And all the locations are using the toolchain, so it becomes a standard inside the company. And it's still in a rollout phases, so there are a lot of locations that's just starting using it, so it will become more and more user. So this slide is a short overview about the different parts integrated in the platform and also the tools around the AVLab platform. AVLab is based on the MATLAB Simulink. So I start from the top of the column here. So we have one part that handles synchronization with our data management and architecture tool that is by Visuity called ADD. So this is a really important part that we have a seamless integration and synchronization feature between the Labs repository and the MATLAB workspace and the Simulink model. Then we have one other module that deals with the generation of test vector in a graphical way, also with the possibility to import data from measurement, for example. Then the biggest part handles with the testing part on a model-based MATLAB Simulink environment. So this is not only just about running tests automatically, but we have also easy functionality for doing regression testing or back-to-back testing. And the other part is dealing with code generation. So here we support and have to support the two main code generator. Another part deals with consistency and review. I will go a little bit more in details later on in the talk. We have another part that handles the aggregation of components together in a convenient way for the user. Then we also linked the AVLab to the Simulink verification and validation model coverage feature so that we can also gather the model coverage information. And we have also one part dealing with modeling guidelines. And for the static check modeling guideline, we use an external project by MAS called MExam, or the newer version is called Drive. Then we have below some other key feature like renaming part that allows us to rename labels really comfortably throughout the whole files belonging to the component. We have one part for delivering the work product to the customer, also in a AVLab free way, so pure MATLAB Simulink. And we have also one part that deals with collaboration scenario. Transversally, we have implemented also batch framework that allows us to run through the whole component tree recursively batch actions, so they can be pretty everything, like testing or like reviewing. So this is a good framework, like also performing consistency check through the whole project tree. Another key tools that is strongly integrated with the development platform is dealing with the application lifecycle management part. So internally we use PTC Integrities, former also known as MKS. And here we have also an integration with requirement management part, configuration management part, and also test management part. So the advantages that brings the toolchain and the standard platform we are using. So before AVLab, the main picture, if you can show the slide, I would just go to the visual picture. The users were pretty crazy because they were lost in, there were no guidance in using the toolchain. And also we had many tools that were not really connected together, and it was really hard to switch between tools. And now with the introduction of the toolchain and the platform, we have really established one way of doing model-based development, and we also have a real platform. That means one platform from which you can start different tools, but they are really connected together. And this naturally increase the efficiency and the productivity and also the quality of our development. So this slide is a plot between the different test platforms we can use by doing model development and also the system level that are under test. And the main challenge that was also mentioned in the masterclass by Megan is that we would like to do test front loading. So that means we'd like to test as far and as much as possible and as earlier in the development process. Main reason is to improve the efficiency and detect bugs earlier. And for this, you see on the left corner, this is the part that can be run under MATLAB Simulink, so from mill to seal and peel. And a challenge is becoming when you try to increase the complexity of the system you are testing. So if you start from the unit level, the software component, this is pretty easy to handle in MATLAB Simulink. But if you go to the full software system, then it becomes more and more complex to be able to run the simulation under MATLAB Simulink. So to support this front loading, we had tried different approach, and one approach is to have an easy aggregation feature. That means that we can build under MATLAB Simulink composition of different components in a semi-automatically way. And the other approach is to face the performance issue that comes when you're handling big system in MATLAB Simulink. And for this, we have forced the use of Windows 64-bit. We have also pushed the use of reference model instead of a Simulink library. We are also using accelerated mode. And we also introduced simulation parallelization framework where we now are able to run a test case in a fresh MATLAB instance for each test case, and this allows us to reduce the out-of-memory issue with encounter without doing parallelization. So here are a short list of challenges we face. It may be familiar also to some of you. So for today's talk, I pick up some topics mainly related to the consistency and the traceability. And I would like also to talk a little bit about the aggregation part, the aggregation feature we implemented. So if you are interested in other topics, as I said at the beginning, you can contact me for a special session. So prerequisite for handling in a convenient way traceability and also for the pushing the performance limit is that we've established a lean data management and lean. With lean, I mean that we prefer to split the files in small parts instead of having a monolithic approach where everything is put in one file together. And one part of the data linked to the development is regarding the specification, the test specification. And here we have the approach that we use one directory, grouping all the files belonging to one test case, and there are pretty many. The advantages of this approach is that we have a direct access to the information. So for example, we have one file that contains the stimuli, the test vector for the test, and it's available directly locally and can be then used directly while doing the test harness before starting the test. We have also this way a straightforward reuse of test cases. It's almost only a copy-paste of test cases. And we also can establish here a traceability between the test case and this specification file. So here we use also an integrity feature called source traces to make the link between the two sides, so the configuration management side and the test management side. Other aspect regarding data management is the handling of the simulation data. So here also we are going to a single file approach. That means for each test case simulation data, we have one file, and to ensure the consistency with the test session, we then zip all the files together in one zip file. So that's marking that they belong together. We also have the feature that in the case that we run a further test but haven't changed the system under test, then we can merge also these test session results together. So this approach assures, of course, consistency between the test result and the test session. And it's also advantages regarding the memory handling, so that then when you do evaluation, we only load the required data. We don't need to load all the simulation data belonging to one test session. And this also has the advantage that we can do a parallel simulation conveniently. So here one slide to highlight this component aggregation feature. So this is really shortened to one slide. Basically, the user starts from what we call a project user interface. You see on this project tree on the left that display all the components belonging to one project or one software release, I would say. And from this interface, then the user can select the components he wants to test together or to build together. And then automatically we will build the composition model, and also we will build together the data files. So for the model aggregation, this is a semi-automatic way, because at the end the user still have to manually finish the scheduling between the components. So it's a little bit of magic, but we cannot do everything by magic. And for the file aggregation, also here we aggregate the data files. That means where the labels are defined. And for titling, also the DD files are merged. And we also aggregate together the calibration file. And we can do this in a dynamic way. That means that it's more a call by reference. Or we can do this in a static way where we just extract the content of each component data files and include them in the aggregated data file. So now I move on to the traceability and consistency topic. So here we heard today a lot about ISO norm, and there is also another aspect. This is an Automotive SPICE requirement, and with the new version of Automotive SPICE, the 3.0, there is a strengthened focus on consistency that was added as best practice. So you see the blue one are the best practice for traceability, and the red one are the one for consistency. And it is becoming a huge challenge to ensure consistency and traceability everywhere. One feature we have in the platform is regarding the traceability with the system under test. So here the challenge is to be able to find in all the test work products that are created, to find the source of the system under test, and here with real revision traces about which which files were used for testing. We had a lot of, it was an incremental way to reach to the final solution. Because of the time, I will just go through the different steps and highlight the final solution. So we started by using the keywords property in the files that are automatically expanded when you make a check-in in the configuration management. But it was not working because if you modify then locally the file, then you lose the consistency with the revision. Then we thought about downloading the revision from the version management repository and then test again this downloaded revision. So with this way we were sure that we were testing against specific revision, but it is quite cumbersome to download this file and then redirect everything to these downloaded files. So we now came to another solution, that is that we, while working locally in your sandbox, we gather the revision information on the fly, and we also mark if the files are synchronized with the configuration management or if they were modified. And if they are modified, then this is not a strong trace. We call this a weak trace. And we will highlight this as something to fix. And for the solution 3, then to clean up the weak traces, before you had to check in and then rerun the test. And the final solution we now came to is to use the solution 3 and also automatically repair the weak revision traces to avoid having to rerun the test. So this is what I've illustrated here on this slide. So basically, if we check that after the check-in, the files were not modified, then we will repair the weak traces, here in this case 1.11 to clean traces 1.12, and this will be repaired everywhere in all the artifacts, and we don't need then to rerun the test. So this is the advantage of the approach. Another part regarding artifact consistency check. So here the challenge is when you look at the final delivery or at your actual development status, to be able to say if all the artifacts are consistent together. So here I take some real example from the practice. For example, it happens a lot that if you modify the model, for example, then you forget to update the documentation. And this is something we want to be able to check in an automatic way. Also, even if you didn't forget to update the documentation or to regenerate the work products, whatever they may be, it happens that, for instance, the user forget to check in the final product, and then at the end in the delivery, you don't have the expected work product. So for being able to check this consistency between all the artifacts, we've established some kind of tracing feature. Basically, the two main repositories with this revision information are coming from our label management repository, so ADD in our case, and also from the version management repository. And while you create some artifact based on the input artifacts on the left side, then we'd like to trace the source of the input artifact inside the output artifact. And the creation of artifacts can be manifold, so you can generate, for example, a documentation, or you can update the test report, or you can run a test, or you can also generate a code. And then we'd like to, by this tracing mechanism, to be able to identify what were the source used for generating this work product. So here is an example of the consistency check matrix or report we are able to generate. So I take only the top example. So you see on the left column, This is a list of artifacts that are contained in the component. And the top row highlights the revision to the source file and also the information to the ADDA, so the labeling repository. So here you can see, for example, on the row 6, that the test report was generated with a model revision that was 1.3, and the current version of the model available is 1.7, so that we can see that the test report is not consistent with the model, and this is something that should be fixed. Okay, so to conclude my talk, a short outlook about the next step and the roadmap regarding our platform. So for this year, the major milestone will be to finalize the interface to the integrity test management part. And also would like to be able to run review and consistency part automatically. So this is something that we'll integrate in the MES exam tool. And the advantage is by doing the review that we are also capable to automatically fix some findings. This is a strong advantage of this tool. Of course, we are dealing with hot topics like AutoSAR and multi-core support. These are big challenges, and we haven't finalized workflow how to handle this. And we're also working on establishing the continuity between the MATLAB Simulink platform and the other platforms, so especially toward the hardware in the loop platform and also virtual integration platform or co-simulation platform. And for next year, we plan also to use continuous integration, but not immediately for testing part, and more for the review, automatic review of the component, so that we can have key indicators about the development status in a project. So my conclusion, I hope I could give you an impression about our platform. So this is purely implemented in MATLAB Simulink, but it also connects many tools together. And through the platform, we try to provide a best practice, state-of-the-art solution, and also to face many challenges and provide solution to our end users. Okay, thank you for your attention.